So I think we're good to go. So we'll go ahead and get this evening started. Welcome all, and thanks for joining us for our webinar. I'm Dr. Lisa Hicks, the chair of the Sustainable Product Design and Innovation Program here at Keene State College. We call it SPDI, or SPDI for short. In this webinar, our upper level SPDI students will be sharing their great work from last semester in one of our capstone courses, Manufacturing Enterprise. This year we have 4 groups of students who designed and developed a product. They figured out how to manufacture it. They created a pilot run of their product designs and finally worked on the marketing and selling their products. We also have a short recap from one of our seniors who took the course last year as well. So this course, Manufacturing Enterprise, is an example of experiential learning, which is considered a high impact educational practice. The students' experiential learning in this course helped them pull together the knowledge and skills they've been building in our program. They've also built skills in teamwork and project management. I'd also like to announce that we are planning to return to holding our SPDI Senior Portfolio Review in person this year. It'll be held Wednesday, May 4th at 5 p.m., followed by a dinner for our industry partners and friends, and engaging in their feedback on our programs. So save the date and look for emails from me for this May 4th event. Now I'd like to introduce Dr. Hassan Habib. We truly appreciate his expertise in manufacturing engineering that he's brought to our SPDI program, along with his great energy. He was the high impact instructor for this course. Dr. Habib.
Thanks, Dr. Hicks, for introducing me with good words. I also want to thank you all for joining us. It was really satisfying to see how students group worked together to generate their ideas, followed iterative processes to build prototypes at least 6 times before coming up with the final design and manufacturing processes. This was possible because of the combination of various tools and techniques they used, such as computer-aided design software, lean manufacturing concept, quality control techniques, specifically fishbone diagram to analyze root causes of any problem they were experiencing during the prototyping stages. So they used several additive and subtractive manufacturing machines to fabricate their final product, and they needed to track the work hours and material cost as a part of their accounting work to analyze the viability of the business they want to do with the product they designed and manufactured. As an instructor, it was so satisfying seeing the final product like towards the end of the semester. I'm pretty sure they got even more satisfaction than me when they saw their final design thinking converted into a final product. It would be not possible without the continued help of our very own Warren and Curtis. So they were always there when students needed them. So I really want to thank them. Thank you, Curtis and Warren. I'm sure this experience from design to prototype to manufacturing of a product will help our students in future. So I want to thank all audience again for joining us, and I will ask you if you have any comments, any questions, please write them in the chat box. Thank you again.
All right, hi, I'm Kyle.
Hi, I'm Ian.
I'm Ryan.
And I'm Palmer.
And this is the SPDI Dry, a 3D printing filament dry box. We are going to play a quick promotional video to showcase the SPDI Dry and its functionality. All right, this is a showcase of the final product, and this features our SPDI Dry system hooked up to an Ender 3 3D printer in the SPDI lab. And we're going to move on to the research and development. This is our prototype progression of the SPDI Dry from initial ideation to final prototype. We started out large and scaled the design back based on the needs of our target user and test data.
The laser cutter played a huge role in manufacturing the SPDI Dry. We had to run various tests on MDF to get the cuts to come out as intended. We then made a test cube with finger joints to test the fitment in the paint and primer.
We wanted to test to see just how much typical filament, PLA in this case, was affected by water and moisture. We left some filament in water overnight and printed with it versus the same dry filament to see the difference. We also tested the SPDI Dry to ensure that it was absorbing moisture inside the box and keeping the filament dry.
This slide shows our list of materials required to build just one SPDI Dry box, as well as the suppliers and our part numbers.
Process and final production. Here is an overview of some of the Gantt charts we created during the creation of the SPDI Dry. We made a Gantt chart weekly to organize the work that needed to be complete to finish on time. This is a closer look at one of the Gantt charts from the previous slide.
This slide shows an example routing sheet for our front piece of acrylic. It shows the times for each step in setting up and cutting out each piece of acrylic.
Here's an example of one of the process sheets we created for manufacturing the SPDI Dry. This is a summarized version of our manufacturing and final assembly process. This is an example of one of our work instruction sheets. This process shows the steps needed to set up and run the laser cutter using an imported part file from Rhino. This is work instruction continued, showing the laser cutter finishing a side of the SPDI Dry and what the final assembly should look like. Here's our workflow when using the laser cutter. It shows how the model is taken from SolidWorks and then exported into Rhino, and lastly imported into the laser cutter software to be cut.
This slide showcases our workflow when using the 3D printer. The models are exported from SolidWorks as an STL file and then put through slicing software to be printed. These parts are then cleaned up once they have finished printing.
This slide showcases our gluing process for both the MDF and the printed PLA parts. We created custom jigs to ensure the gluing process was fast and precise. This slide showcases our sanding process once the MDF parts are all glued together. And this slide showcases the process we use to both prime and paint the final boxes.
These pictures show our final assembly of the 10 boxes. In these pictures, we are fitting the top acrylic, adding the fittings, gluing magnets, and inserting the sensors. This slide shows examples of quality check sheets we use for each part in final assemblies. The pictures on the slide show an example of a passing or failing part. During our manufacturing process, many pieces didn't pass inspection, forcing us to start over and make a new part for the final assembly.
This is our accounting slide. This slide showcases the breakdown of our individual costs as well as our final cost for creating 10 of the SPDI Dry boxes.
Here's our fishbone diagram to identify our main issues in the design and production of our product. The main problem in production was the inconsistent laser cuts due to the laser cutter settings, MDF density, and thickness of the MDF. The critical path diagram helps show and estimate the total time from start to finish to manufacture one box. Laser cutting, gluing, and the finish process were the most time-consuming, making the bottom path our critical path.
This learning curve is based on the first production model, taking 12 hours from start to finish to design and manufacture with a learning rate of 80%. With this learning curve, we were able to get the last box down to around 6 hours per box. Our biggest takeaways from the project were how important teamwork is in a manufacturing setting and how difficult it is to bring a product to life from scratch.
Hello, my name is Amr Abatello, and I was the project manager for Safe Launch, the Kayak Caddy. When we were first coming up with ideas, my mother told me about her sister, who, due to an ongoing medical issue, didn't have the ability to get into a kayak anymore when they went on their vacation to Cape Cod, Mass. It's always been a tradition for my family to go there and enjoy the lakes. Many people also have this issue. They want to enjoy kayaking, but they can't kayak, not because they can't actually use a kayak, but because they can't get into or out of the kayak. Our plan was to take the entire process of entering and exiting the kayak out of the water where it's safer, steadier, and doesn't require balance or even stepping into the kayak on one foot. That plan led to the safe launch. My team consisted of me, the product manager, as well as a design engineer, Albert Mejia, an accountant slash quality controller, Max Thurston, who unfortunately was not able to come today, and finally, our manufacturing engineer, Ryan Murphy. We will begin with research and development. Here, you can see our progression of models. Included here are prototype 1, 3, and 7, which through their progression met more and more of our design requirements, including serving as a stable base, accommodating different kinds of kayaks, being relatively lightweight, having a rigid structure, and being water resistant. Seen here is the first time we actually attempted to ride inside the kayak, which looked really good in the photo, but about 10 to 15 seconds later actually ended dumping me and the kayak across the floor, which led us to some insights about how much structure and strength we were going to need inside the actual device.
So here we have our final CAD model. It helped us, it met all the functional requirements, and it helped us look at different lengths and widths that this product wanted to be. And it helped us assign where the fasteners wanted to go. And we have an exploded view, but we didn't include that because it has a lot of little fasteners and you just wouldn't be able to see it. And on the right side, we also have the final render of it, which is like the beauty shot of it. And it came out pretty well. So these are some critical features about our production model. I'll be going from left to right. So the first top left you see right there is the handle, and you can adjust it, the height of it, to accommodate for different heights of different people. And our manufacturing engineer, Ryan, he actually knurled the handles and did a pretty good job on them to add some extra grip for the users. Going down, we have a rigid base to support the user of the kayak. We tested it with all different shapes and sizes of different people, and they all held together. Then we have the top right, we have the bungee rope that holds the kayak from sliding when you pick it up. As you can see, we went with more of a wheelbarrow type design. And we also have probably the most critical part is the kayak supports, which hold the kayak snug in place and keeps it from tilting. The build.
One of the materials we used was aluminum tubing. It was kind of a funny story because we knew we wanted to use the aluminum, but we couldn't find it, a supplier for it to get it online. And one day Al was driving to class and he saw a truck with like metal supply on the side and a phone number. So we called him and we ended up getting it from there. And it was like actually more affordable than we thought. And it ended up working out pretty well. We had some extruded T-slot aluminum, which we were able to get from a local junkyard. Aluminum flat stock from Home Depot, and PVC boards, and our coated PLA prints, and also stainless steel sheet metal. And for our seat, we used birch plywood. So some of the manufacturing methods we used, all the metal work was done. We had everything was faced off. It was cut rough first, actually, on a horizontal bandsaw, and then it was faced to the proper lengths on a milling machine for the square stock, or for the T-slot. And the tubing I faced on the lathe to the proper dimensions. And also, as Al mentioned earlier, I came up with the idea to put knurls turned into the handle on the lathe, and it just kind of, when you're pulling someone out of the water, it really gives you the hand grip so it doesn't slip out of your hand, especially if your hands are wet. There was a decent amount of woodworking for the seats. Everything was just cut out and sanded and then painted, or actually finished. And yeah, we painted our logo on the seats as well. So here's some of the templates we used. These really helped us when manufacturing to make, large quantities of the exact same part. You can see that we would use usually a marker to trace them out on the whatever kind of stock we're using. The 1A and 1B was the PVC, and we used the aluminum for the brackets, the other brackets. And then number 5 is a stencil we used that was laser cut on our laser cutter to paint the logo on the seats. And that's just a blown up picture of the logo that we came up with.
Here, you can see some of the 3D printed components that we used on our final model. Above, you can see the specific settings that we used to achieve the maximum strength and durability for these particular components. We used PLA filament, which was then sealed and painted by our design engineer, L. Here, you can see our purchased components that were unaltered. So these include hinges, wheels, fasteners, and as well as our alignment markers, which made up a good portion of our budget, but they also allowed for us to get some really consistent parts as well as making the total product look very nice. Next, we have the all-important documentation, helping us keep track of costs, goals, and time.
So here we have our Gantt chart, and this is basically an overview of the whole project, and it's split by week to week, and each week we write our task for that said week, and it kind of shows us, keeps us on track of what we're doing well and what we finished and kind of which task we're lacking in. And it kind of gives us an overview of what to pick up and what we really need to focus on for that week. And we did that throughout the whole duration of this project.
Here we have the critical path, which allowed us to figure out exactly what processes within our final assembly and production we're going to take the longest and which we're going to kind of take the shortest. So as you can see, the one red line goes to F. F is essentially standing in for our printed brackets. And because of the overall print time that those took, those ended up extending all of our activities by the most. That way we knew that in our final production run, we really needed to get those prints in first. And that way everything else could happen while those were printing and we wouldn't get behind on our production.
So this is the routing sheet. It's basically a sheet that tells us how to manufacture each part of our product. It basically helps us keep track of the process and make sure it's consistent for every part. It tells us what tools we need, what machines to use, and a rough estimate of how much time it takes. And this sheet is the work instruction. It's basically very similar to the routing sheet, but it includes pictures and measurements and it improves consistency in our manufacturing process. So this is the bill of materials and the quality control sheet. It gives a complete list of all the components, their part numbers and routing numbers. The routing numbers obviously go to the corresponding routing sheets. And the quality control sheet basically gives the tolerances for each part, and you can fill it out when the parts are produced. You check each part and make sure it's a good part. Basically at the bottom there's a pass and fail, and if it doesn't fall into the tolerances, it'll not be a part that's used in our final product.
So during this project we had to do an aspect of accounting, and we listed all of our materials and each cost for each of those materials and the quantity of how many we needed. And here is an example of actually another Excel sheet that we use for another class that helped us keep track of one unit and how much it would cost to produce, from a material standpoint, produce that one unit. And the total came out to $216.91 for just one production model of this project. And we also have made an equation that helped us split the total cost of all the materials that we bought for this project. And it helped us split that evenly for the group. And this is a fishbone diagram. I'm sure you guys in the industry know what this is. It serves as a great visual way to look at cause and effect, and you can do root cause analysis and get to the the real big issue. So thank you for listening and tuning in to our project presentation for the kayak launcher. We had a lot of takeaways during this project. One of my takeaways was I like the working as a team. During my school experience, in my 2-year school, we didn't really get to work as a team. Most of our projects were just solo based. So this right here was really cool to work together with other students, because I know that's how things happen in industry. So that was really cool.
Amr again here. I also had a lot of takeaways, but I think my biggest takeaway was just how many challenges are really present when you're trying to bring a product to fruition, and particularly to manufacturing. So we ran into a lot of issues with sourcing, with consistent construction, as well as just finishes and material needs. So a lot of those challenges taught me a lot of things, and I think that's one of my biggest takeaways.
Ryan again. One thing I really enjoyed with this project was we got to use recycled materials. We got to go to the junkyard and pick out materials that work for us. And I also did like working as a team as well. I liked how I learned how fasteners and taps interact with getting everything to all fit together and getting the right fasteners for the job.
Hi, I'm William Mullen. I worked on this project my junior year, so some of you may have seen this product last year when the seniors at the time presented it. I'm going to be talking about the area of the project that I focused on, which was the electrical. For our project, we built a set of 10 pendant light fixtures. We decided on a Danish modern design style. Here you can see a few renderings done in SolidWorks of the finished product. We began with ideation and prototyping. We initially started out with cylindrical design, which proved to be very difficult to manufacture with the wooden veneer shade. It also had other design flaws, such as it was difficult to change the light bulb within the fixture, and it had poor display of light on the inside of the shade when it was illuminated. Then we moved to a more unique oval-shaped design, which allowed us to use LED light strips to display the light evenly across the shade and require less bending of the wood veneer for manufacturing. For the internal electronics, we used LED light strips for the light and connected them using proper LED light strip connections. We also installed a wire strain relief using heat shrink on the wire's insulation to comply with UL standards. We needed to house the transformer in the canopy of the light, so we were able to 3D print a custom mount and use number 6 hardware to fasten the transformer to the mount. To attach the transformer to the E26 light bulb adapter and abide with UL regulations, we use metal wire crimps enclosed in heat shrink to protect from moisture and risk of shock. The benefit of using an E26 adapter is that the consumer can easily install the light into a typical frame-in fixture in their home, or cut off the E26 adapter and have it professionally hardwired into their home. On the left side is a photo of the canopy electrical being installed with the work instruction. This was the final step in assembly, and on the right is quality control testing of the fixture in our shop. This graph displays the amount of labor hours that went into producing the light from design and manufacturing. As you can see, the electronics took the second longest amount of time to engineer and create. And finally, here are some photos displaying our product installed in a home. It also shows the light being displayed evenly across the shade, as well as the light being emitted from the bottom of the fixture onto the table. Throughout this project, I learned a great deal about electronics and their regulations, as well as how to work with wooden veneers. Thank you.
Hi, I'm Nathan Maxwell. I'm the design engineer for the Chaotic Motion Group. I'm joined by Sam Cloutier, our accountant and quality controller, Catherine Orlier, our manufacturing engineer, and Samuel Foley, our project manager. Our initial goal was to make a pendulum-based art piece that contained good motion and was visually appealing to look at. We had a couple design requirements, including lights and a chaotic motion machine. And it needed to be capable of human interaction, such as touching it or just moving it.
So this is our promotional video. It's just a shortened down version of it.
couple photos of our prototyping process. On the far left, you can see the initial concept modeling we did. It was very rough, but it gave us the idea of what we needed to do to get into the initial prototype stage, which you can see right in the middle. And as we progressed further throughout the semester and further in our work, we ended up on the final prototype. That was our production prototype, as you can see on the far right.
Our construction process, so the first part is our acrylic arms and our acrylic circles. 2 is MDF, which is the backboard painted in black. 3 are the bearings we repurposed from fidget spinners. 4 are bicycle lights for color and aesthetic. And 5 are the magnets.
This is an example of one of our control processes. We use this in order to stay on track of the work that we need to do each week. It allowed us to keep track of what we had finished the week prior, what still needed to be done in the next week, and where we were in regards to the total project.
So this is the bill of all of our materials. So in the yellow area is just our big project as a whole. Then in the green, all of the smaller components. So the acrylic arms, the acrylic center arm, backboard, the bottom plate, the motor, and then in the blue section are all the materials that each part is made out of.
This is our fishbone diagram. Our fishbone diagram goes over any issues we had with fitment and design improvements and all the factors leading up to that. Those being time, manufacturing, design, material changes, and other production problems. Some of these include problems we've had with 3D printing, fitment issues, tolerances, material and design changes. These are our quality assurance sheets. Each part leading up to the final production model, and each production model goes through a test and has to meet certain expectations, certain quality control factors in order to be passed and moved on to the final product, and in the end, be ready for be shipped out.
This is the readout for our final materials costing. This specifically shows the costing for our final production run, not any of our prototyping. The cost per unit to recover all funds spent on prototyping and final production runs brought the cost per product up to $65 per unit.
Throughout the entire project that we did last semester, we learned many things, from a lack of communication causing error to supply chains causing issues and parts coming in time, to design changes that influence how we purchase materials. We did nothing but learn the entire semester. We also learned the importance of marketing at nearing the end of the project. And if anyone has any questions for us after the presentation, we'll have a Q&A. There's a bit you could put your questions in. Thank you.
Hello, thank you for taking the time to watch our presentation. We are the OYA Fire Pit Group. I'm Cartwright Nelson, the project manager, and I'm joined by John, our design engineer, Sam, our accountant, and Brian, our production and manufacturing engineer. Our goal for this project was to create a fire pit that had a lot of benefits over normal fire pits. We wanted it to be smokeless, sustainable, burn faster and brighter than other fire pits, and have a cool factor so that you had something exciting to look at while you were hanging outside with your friends. We utilized recycled stainless steel kegs from a scrapyard in order to save money and reuse old materials so that we weren't wasting as much. And we used a vortex technology so that it was easier to light, had less smoke, and created a more visually pleasing fire pit. For prototyping, we started out with cans from canned goods and a drill. It had a double wall system, but the first prototype had a lack of airflow. So from there, we moved on to bigger cans, added a propeller type intake at the bottom, and angled fins for the air to come out of, so that you can see that it does have more of a spinning effect and a brighter burn. The third prototype, we moved to a full-size model, and it worked very well, but we had some issues still. So on the fourth prototype, we shortened it, added some new features, used metal tape to try to seal off some of the airflow, and found out what worked and what didn't work. We then had to take that whole thing apart and build our production prototype, which didn't actually end up being the production prototype, but it accomplished what we wanted to. So from there, we just had to work on the overall design and visual aspect of our fire pit.
This is our initial design. It's the first design that had the fins that create the vortex and the lower intakes that updraft to create the smokeless effect. And on the left is a 360 of it and our sketches. And on the right, you can see the entire fire pit cut in half, so you can see how it functions from the inside. Okay, so this is our final design. The biggest change is the top, which has this uniquely shaped circle that we made into our logo. And it's finished with a radial brushed effect, and has the logo painted out on the outside on the stainless steel. And on the back, we put the custom laser engraved warnings for how to use the fire pit, along with our names, model serial number, and when we made it and what we named that specific pit. And here you can see all of the custom paint jobs that we did for each customer as they wanted them.
I'm Brian Everett, and these are some of the manufacturing processes that I want to highlight. So throughout this whole project, some of the processes we used were MIG welding, spot welding, laser cutting, plasma cutting, and knockout punching. And at the beginning of this project, none of us had a ton of experience with any of these processes. So we did learn a lot throughout this project. These are some of the jigs and templates we used throughout the project. On the right are templates that we use to mark out locations of holes, cuts, and bends on sheet metal. And then towards the left, we have our keg cutting jig, which utilized a plasma cutter. So I made a custom mount for it where we could actually fine tune the distance of the nozzle to the keg in order to adjust to get perfect cuts. It ended up working out pretty well. It requires 2 people to operate. One person pulls the trigger of the plasma cutter, and the other stands opposite them and slowly rotates it by hand. So our original production prototype was made out of mild steel. Everything besides the keg was mild steel. So it required paint so it wouldn't rust. And we were using flame-proof paint, but it didn't end up adhering well. We prepped the surfaces very well. We sanded and cleaned everything prior to the painting, but the paint still didn't end up sticking well. So then we had to make a decision whether to keep on testing out different kinds of paint or switching our material to stainless steel. That's what we ended up doing. We switched to 304 stainless steel because we figured it'd be worth it because we'd have a higher quality product in the end. So throughout this whole project, we ran into a lot of manufacturing difficulties. These are just a few that I want to highlight. So one of our biggest problems was the intake holes on the exterior. We were using knockout punches to punch these holes, and the 304 stainless steel was so strong that it was just it was dulling them very quickly, and we ended up breaking a couple of them. And they were really expensive, so we couldn't buy more. So we had to figure out other means to make these big holes. Yeah, just the strength of the 304 stainless steel in general kind of made everything more difficult. And another problem we had was all like the small tolerances of all the small fins we have going around the perimeter of the top. Those were very hard to get all lined up properly.
Yeah, so this is our website and store. We put this up, I think, towards after we got the production model ready. We put this website up just so that our customers could go look at it and get a sense of what we're going to be selling them, and also keep them updated with the progress on our project. So our final production run produced 8 fully finished stainless steel fire pits that you can see right here. And there's also a couple other pictures. The one on the bottom right corner is me and my dad testing it out outside at my house on a very cold night. And another one above is one of our professors using it with his family on a snowy day. This is our full bill of materials for a singular unit. So I'll just leave that up there for a minute for everyone to look over. This is what it took to make one unit. Next, this is our full accounting records of our costs. And we also did some calculations on how much it would make to produce a single unit in the next run, now that we don't need all the funds for testing and don't have to buy all the equipment again. To finish this off, we have one of our promotional videos. The rest of them are up on our website. Before we get into that, I just want to thank you all for listening to our presentation, and we'll be free to answer any questions you guys have after all the presentations are over.
Life doesn't always give you lemons. Sometimes it gives you wood. And the best place to burn that wood is in the Oya fire pit. These handcrafted works of art are forged from recycled stainless steel and built to withstand whatever you can throw at it. The Oya fire pit uses vortex technology for the most flamboyant flame in the industry. Oya fire pit. It's like regular fire, but with a twist.
So thanks, everyone. So I'd say that the students really have illustrated the many steps it takes to take an idea all the way through to a working product. Lots of problem solving there. So my hat's off to all the students. And also to Dr. Habib and to Curtis and Mead and Warren Hurd, our amazing lab managers and skills instructors. I'm also really impressed with the skills the students have developed in new product design and development, in manufacturing processes, and in manufacturing management. So, so please feel free to put any questions into the Q&A. I think there's some we can start with here. So I think this one would be good for Brian Everett. If you were going to make more of the Oya fire pits, is there anything about the manufacturing process that you would change?
Yeah, it'd probably change a lot. We built them all by hands, so they took a long time to make, and we didn't end up making too much money total on the project. We were like, I think we each made like $20 profit for the entire project, even though we put in like hundreds of hours worth of work. So we definitely need some automation. We'd probably need like a giant plasma CNC table or something.
Great, thanks. Okay, so how about this one could be for Palmer. Let's see, on the SPDI project, was there a specific piece that repeatedly failed inspection?
Yeah, I would say that for us, one of our bigger issues was the MDF. When we would cut it out, we were having a lot of issues getting consistent cuts with the laser cutter, which was giving us ends that were really burnt, or we would have to cut through multiple times, which led to fitments that weren't always correct. So a lot of the MDF had to be recut over and over again. So yeah.
Okay, great, thanks. All right, let's see. Here's one related to the Kayak Safe project. How about Albert for this one? What was the hardest design challenge with the Kayak Safe project?
We had a lot of challenges with this project. I would say one of them would probably be incorporating like a stopping mechanism or like a braking system for it, because obviously you don't want it to like roll away while you're in it. But with our like more like wheelbarrow type design, I think that excused the need to implement like a braking system and add more complication to the whole project.
Yeah, thanks. And yeah, challenges to solve, yes. So I've got another question here. Let's see. How about, let's see. So we have a question here that anyone could answer. How did the experience influence your thoughts or plans after graduation? So anyone want to jump in there? How about Ryan Bevins?
I'd probably have to say that I'd probably want to be on the managerial side of things. Just because I just feel like it would be a better fit for myself after going through this whole process. You get to see all the different steps, and I enjoyed that process a little more than anything else.
Great, thanks. Anyone else want to add to that? Anyone else have some reflections about how this project influenced what they want to do after they graduate? How about Carter? Any thoughts?
I would say probably designing things and being able to actually prototype them and build them myself was really gratifying. Was a tremendous amount of work, but once everything was done, it was pretty awesome to see how much we got done, because at the beginning we really didn't think it was going to be possible.
Yes, okay, so how about, here's another question. How about for William? Let's see, and this can also, anyone else that wants to jump in there. What would you tell a high school student who is considering the SPDI program as a major? Anyone? So William, if you might be able to jump in there, and is there anyone else that could follow up with him after him?
Yeah, it's definitely a good major. You learn a lot on both the designing side of things using CAD drawings, and then you also get to actually go into the shop and experience making the things that you design. So I think it'd be really helpful for anybody who wants to become a product designer. You get to know what you're designing will definitely work when it ends up being built. So you're not building things that are impossible to actually manufacture. And yeah, it's definitely a great major.
I'd like to comment as well.
Okay.
Well, I worked an internship over the last couple of summers, and I worked with, a few different coworkers who all were majoring in like mechanical engineering type things, and they had the skills when it came to doing things on the computer, but when it came to actually putting things together, like physically hands-on, they didn't know what to do really. The SPDI program gives us, experience on the computer and in the shop, because if you design something and you don't know how to build it, you can't design something. Let me rephrase. You can design things that can't be built if you don't know what you're doing. You can't drill a square hole, basically, is what I'm trying to say.
Yeah, great. Thanks. Great insight there, Ryan. Okay, so I've got a question here about how did the groups decide the topics of their project? What was the inspiration behind them? I'm thinking, Amr talked about the inspiration behind the kayak safe. And so maybe maybe John could talk about the inspiration behind the fire pit.
Oh yeah, for us it was the tornado spinning aspect of it that really drew our attention in. Carter came up with the original idea of it, and we all saw it and we're like, well, we're gonna jump on that, and it kind of created a theme for our group. We're kind of all the same kind of just crazy people that want to make fire, and it shows in our designs and our videos and everything. But yeah, it just looked awesome, and that's what we wanted it to be.
Great. So how about Kyle on the for the Speedy Dry project? What was the inspiration for your project?
So one of the biggest things for the Speedy Dry with me is like the 3D printing, you know, and the Speedy Lab is really awesome. I love being able to take something from the computer and, you know, put it, you know, and make it in real life. I think that I noticed there's a lot of people that are having issues with like old filament and stuff just from like being part of like the 3D printer community and just like looking at stuff online. And so I knew that we needed a solution in the Speedy Lab. So for one of my ideas, I just kind of submitted it, and then, you know, people liked it and we just rolled with it.
Okay, and then let's see, how about Sam Foley, maybe on the inspiration for the chaotic motion machine?
Sure. So this was originally my product proposal, as well as a few other people who have spoken about theirs now. I find myself pretty commonly watching sort of interesting mathematical videos and stuff online, and I had found one about the motion of a double pendulum and how it is proper chaotic motion. And I thought that that video and the motion itself was super interesting. And so the original product proposal was more or less just taking that motion and trying to create an art piece that was easily accessible to people who are both artistically minded and those who may be a little bit more mechanically or scientifically minded as well.
Great, thanks. So I think what this next question talks about, and I'm thinking Amr might be interested in addressing this one. Did any projects have safety concerns arise during prototype manufacturing that needed to be addressed, and that maybe you addressed them during using work instructions? So, and also maybe Brian Everett could also talk to that as well, because I think that you did address those kinds of things. You looked up the safety things and did them, I think. So let's, Amr, maybe you could jump in there.
Yeah, so can everybody hear me? I think I'm being heard well.
Yeah.
So we had a lot of safety concerns with my project, obviously, because our project happened to, actually carry a person, which on its own carries a lot of issues. So most of the issues we ran into were due to strength within our actual design. So those were solved by using more robust components, using thicker stock steel or thicker stock aluminum for certain parts, as well as just beefing up our 3D prints and then any other parts that we had. It was all about creating strength and structure throughout the actual product. In terms of safety concerns with the actual prototyping and manufacturing of the product, I can't say that we had too many. Many of the parts were manufactured by everyone in our team who, like Ryan was saying before, we've all received quite a bit of training on, working with our hands, working with all the tools in the shop. So we all have a pretty good understanding of the safety that is required for any kind of tool. So all of our procedures were generally pretty safe from the beginning. I'd say that the most dangerous procedure that we did would probably be any kind of facing or operations on the lathe, just because when you're moving that big of a piece of metal, anything bad could happen. We do all our best to make sure that nothing bad can, but
there's the most opportunities for failure when you have a large amount of weight spinning like that. But overall, our work instructions kind of mirrored that education we received about safely using all the equipment that we have here at the shop.
Great, thanks. And I think I'll jump to Brian because I know you worked really hard on the jigs and fixtures and spelling out the work instructions for the plasma cutter and some of the other equipment that you were using. Yeah.
Yeah, so our early full-size prototypes were pretty unsafe, I'd say. I know our first one had no legs. I'm pretty sure our second full-size one had no legs either, so it would just kind of singe the grass underneath. We were just trying to build the early ones as fast as possible to test as many things as quickly as possible. So yeah, there were some oversights. Another thing that was kind of unsafe about the early ones was there was lots of burrs and sharp edges, especially on the fins. All the little fins around the top cuts we made in stainless steel were pretty sharp. So we made sure to like sand all the edges and everything, make sure there was no burrs or sharpness.
Great. Okay, thanks. So let's see. So I think, let's see. So we have another question here. Another one about the kayak safe. So how about this one for Albert? What was the hardest? Let's see. I think we already did that one. Let's see. So I think what we might do here is, here's one for about the pendant light. Okay, so how about for William? On the pendant light, how did you fasten the transformer mount in the canopy?
We wanted to be able to make sure it was movable within the canopy, but around the center hole where the wire passed through going down to the light. So we, through very tight tolerance and fitment, made the transformer mount able to snap into the hole out of the bottom of the canopy. So it stayed in place, but allowed it to rotate around inside the top of the canopy. So depending on where in your home you were installing it, it would be able to fit the transformer between the canopy and the, say, in-frame can light.
Okay, thanks. Here's another one. I think I'll give this one to Carter. On the outside of the Oya fire pit, is it hot or is it insulated?
It is not insulated. It had an inner wall, which was the keg, and then the outer one was stainless sheet metal. But the goal was to have that air in between heat up and rush out of the top fins, so the outside does get hot. We had to use flame-proof paint on the outside.
All right, nice. Okay, I think that we've got a really great comment here. I think we'll, unless there's any other comments from, I see Dr. Habib is, if Dr. Habib or anyone else has any comments, I've got a really nice comment here from one of our guests, so I could wrap up with that.
Yeah, thank you. Are you hearing me, all of you?
Yes.
Yeah, so I just wanted to let you know it was a great experience working with them. And this is the third time I tried to teach them. And yeah, I know this is one of the hardest course for me. I'll be very honest with you. But this time it was kind of easier for me because I got them in various other courses. So they knew me, I know them. Sometime I was hard, but I think they understand why I was hard. And at the end, when they saw like their real product in front of them, I saw their like happiness in their mind. So yes, thank you again for being in this course and doing your hard work and making a nice and great product. Yeah, it was a great semester with you guys for sure.
Great, thank you, thank you. So I'm just going to wrap up now, and thanks everyone for coming. I have some great a couple of really nice comments here that I'll end with. So this is from one of our business colleagues here, our industry colleagues. Awesome work, everyone. Great to see the functional videos. This is a great selling point. Nice to see how everyone worked through the different levels of problem solving. This simulates what industry faces every day. If anyone's looking for a part-time internship, contact Victor Kissel, Vic Kissel at Maxis International. And I have his email if anybody wants to contact me. And then we have another, so thanks Vic for that nice comment. And then we have another comment here. This was a very exciting, to watch each group's projects and hear about the different problems and solutions and communication working together as a team. So I think that you all portrayed that, and it sounds like we were able to show that to our audience. So, and then it's thank you for inviting us. So you all are welcome. So thanks everyone for attending, and remember the May 4th Senior Portfolio Review. So look for emails from me, and thanks a lot.